For over 60 years, every single spacecraft that's touched the moon has landed the same way, on legs. The Soviet Luna 9, the Apollo missions, even last year's Odysseus lander. All of them relied on metal supports to stay upright on that dusty lunar surface. But in 2021, SpaceX proposed something that shocked both NASA and China. Landing Starship on the moon without any legs at all. When SpaceX won NASA's $2.9 billion human landing system contract for Artemis, their design broke every rule in the book. No folding legs, no hydraulic pistons, no shock absorbers. Just a massive 9-meter-wide steel hull that would touch down directly on the lunar surface, using the spacecraft's base as the landing pad itself. NASA's engineers couldn't believe it. The Chinese space program was equally stunned. This wasn't just unconventional, it was revolutionary. The potential benefits were staggering. By eliminating landing legs entirely, SpaceX could remove 8 to 10 tons of hardware, pistons, hinges, sensors, titanium struts, all gone. That weight savings translated to 7 extra tons of payload capacity, enough to extend astronaut stays by several days, enough to fundamentally change what's possible on the moon. But there was one massive problem. The moon doesn't forgive mistakes, and NASA's safety board had serious concerns about whether astronauts could survive a legless landing on terrain that varies from rock-hard to powder-soft within meters. Welcome back to Space Update 24H, where we break down the biggest developments in space exploration with the technical details that matter. If you're passionate about humanity's return to the moon and the engineering challenges that make it possible, you're in the right place. Today, we're diving deep into SpaceX's radical legless lander concept, why it was brilliant, why it was dangerous, and what NASA ultimately forced them to change in 2023. We'll also explore an even wilder idea, landing Starship horizontally on its belly, which could have turned the spacecraft into the moon's first instant habitat. Let's dive right in. Here's what most people don't understand about SpaceX's legless lander proposal. It wasn't reckless. It was calculated simplicity taken to its extreme. Elon Musk's engineering mantra has always been brutal. The best part is no part. If it doesn't exist, it can't fail. This principle drove the Falcon 9's minimalist design. It shaped Starship's stainless steel construction. And in 2021, it led to the most controversial proposal in lunar landing history. Landing legs aren't simple metal struts. Each leg is a complex machine requiring folding mechanisms, hydraulic pistons, deployment actuators, position sensors, and control algorithms. You're building an entire subsystem just to touch the ground. Every component becomes a potential failure point in an environment where failure means death. SpaceX's math was stark. Eliminate the legs, remove 8 to 10 tons of hardware, and thousands of failure points. But here's what made engineers around the world pay attention. Those 10 tons translate to 7 additional tons of usable payload. That's not just numbers on a spreadsheet. That's the difference between a brief visit and establishing real infrastructure. Extra life support scientific equipment, construction materials, the margin between survival and expansion on the moon. So how do you land a 50-meter spacecraft on loose lunar dust without sinking or toppling over? SpaceX's answer was plume surface interaction, and it's pure physics genius. 30 seconds before touchdown, while the main Raptor engines throttle down to barely 5% power, a ring of specialized nozzles fires hot gas at 45-degree angles toward the surface. This isn't just clearing dust, it's manufacturing a landing pad in real time. The gas streams compact the loose regolith into a dense layer 20 to 30 centimeters thick, capable of withstanding 25 kilopascals of pressure. That's equivalent to a car tire on Earth. The system could even flatten slopes up to 10 degrees, turning uneven terrain into a stable platform. The spacecraft's base would use a reinforced titanium ring 8 millimeters thick, surrounded by a crushable skirt of 3D-printed aluminum mesh. This mesh acts as a massive shock absorber, deforming in a controlled way to absorb 70% of impact force. During those final 10 seconds, Starship would settle at less than 1 meter per second, gentler than stepping off a sidewalk, one landing system. No moving parts. Just materials science and precision thrust control? If it worked, it would rewrite every assumption about lunar landing architecture. But SpaceX didn't stop there. Their engineers explored something that made NASA's safety board question everything. Horizontal landing. The concept. Starship descends vertically as normal, slowing from orbit with its Raptor engines. Then, in the final moments, reaction control thrusters tilt the vehicle forward to about 30 degrees. It belly lands using a thick composite pad, then fires 4 autonomous anchors into the lunar soil to lock itself in place. This wasn't just creative, it solved multiple critical problems simultaneously. First, stability. A horizontal starship spreads its 50-ton mass across 160 square meters, reducing ground pressure by more than tenfold compared to any leg design. It could land on terrain that would swallow traditional landers. The dramatically lowered center of gravity means virtually no tipping risk. Second, crew access. In vertical configuration, astronauts face a 30-meter descent on an elevator, slow, complex, and vulnerable to mechanical failure. Horizontal? A simple 3-meter staircase. Rovers roll out through side doors. Equipment transfers that would take hours become 5-minute operations third, and this changes everything for long-term lunar presence. Instant base. A horizontal starship provides over 1,000 cubic meters of pressurized volume, larger than the entire International Space Station astronauts could pile regolith on top for radiation shielding. The vehicle becomes permanent infrastructure, not just transportation. For cargo missions with no return flight needed, this design could stay on the moon indefinitely as the foundation of humanity's first extraterrestrial settlement. Then reality intervened with unforgiving force. Starship's structure was engineered for one thing: vertical flight. Its steel frame, fuel distribution, internal systems, everything optimized for compressive forces along its vertical axis. Rotating it horizontal introduced bending stresses across 50 meters of structure it was never designed to handle. In Earth's gravity, it would buckle on the moon. The math was uncertain, and uncertain means unacceptable for human spaceflight. The propellant tanks created another crisis. Liquid methane and oxygen don't behave in low gravity like they do on Earth. They slosh chaotically, creating pressure imbalances that could destabilize the vehicle during the most critical seconds of landing or launch. And here's the deal breaker. Once horizontal, how do you stand a 100 to 200-ton spacecraft back upright for launch? You'd need to build a mobile launch tower on the moon just to get home for cargo missions. The horizontal concept remained brilliant. For Artemis 3's tight timeline with crew aboard, it was impossible. By late 2022, NASA's Aerospace Safety Advisory Panel delivered their verdict on the legless vertical design. Their language was measured, but the message was clear. The risk exceeds acceptable limits. The moon's surface is treacherous in ways that don't show up in simulations. Apollo samples revealed that regolith density varies wildly within meters. Some areas rock hard, others loose enough to swallow equipment a full meter deep. Traditional landing legs spread weight across multiple points and compensate when one leg sinks deeper. Without legs, if one edge of Starship's 9-meter base sinks just 1 meter more than the other side, the entire 50-meter vehicle tilts beyond 25 degrees. In lunar gravity, that means it's falling over. Mission lost, crew in danger, no recovery possible. Then there's the engine plume problem. Even at minimum throttle, 6 Raptor engines produce exhaust velocities exceeding 2,000 meters per second. Simulations showed this carving craters 1 to 2 meters deep directly beneath the vehicle, potentially destroying the compacted surface the PSI system just created and the dust. Lunar regolith is electrostatically charged and microscopically sharp. Once disturbed, it doesn't settle. It floats in clouds that coat sensors, infiltrate seals, contaminate life support, and threaten astronaut health. NASA's human rating standards require minimizing plume effects, not amplifying them. The final nail: fault tolerance. NASA requires 2 levels of redundancy for human-rated systems. In the legless design, a single Raptor engine failure during final descent unbalances thrust with no backup. No structure to compensate one malfunction equals catastrophic crash. So what's the real lesson from SpaceX's legless lander saga? It's this: SpaceX's proposal wasn't a mistake. It was essential exploration of the boundaries of what's possible. That's how breakthroughs actually happen. You push radical ideas to their limit, test them against physics, and discover where the real boundaries are. The legless concept was brilliant in theory, but the moon doesn't grade on theory. The updated Starship HLS with titanium legs might look less futuristic, but it represents something more valuable than innovation. It's the product of hard lessons learned, a balance between bold vision and proven survival. Because in human spaceflight, you don't get credit for elegance. You get results by bringing astronauts home alive. But here's what excites me. This story isn't finished. As we move beyond brief visits toward permanent lunar bases and Mars colonies, these radical concepts, legless landings, horizontal configurations, instant habitats, they may return. When we're building to stay instead of just visiting, those impractical ideas might become the standard. In spaceflight history, no concept ever truly dies. It just waits for its moment. Now your turn. Would you have risked the legless design, or did NASA make the right call? Drop your answer in the comments. I read everyone. If this technical breakdown gave you new insight into lunar landing engineering, smash that like button. Share this with anyone fascinated by the real challenges of returning to the moon. Not subscribed to Space Update 24 Hours yet? Hit that subscribe button and turn on notifications. We're covering humanity's return to the moon with the engineering depth that matters. Thanks for watching. See you in the next one.